Hi everyone! Welcome to this channel. Today, I am going to teach you how to write the quantum numbers of an element using its electron configuration and orbital diagram. So without further ado, let's get started. So first, let's define electron configuration. So in its simplest definition, electron configuration is the arrangement or distribution of electrons in the orbitals of an atom. So this is what an electron configuration looks like. This is the electron configuration of neon, the 10th element in the periodic table. So the 2 here, we call it the main energy level. The P here, we call it the subshell. And the superscript up there, the 6, that refers to the number of electron or electrons in that specific subshell. So notice that all our electrons or superscripts, when added, are all equal to 10. 2 plus 2 is 4, plus 6 is 10, which is equal to neon's atomic number or neon's number of electrons. Therefore, in writing the electron configuration of a specific element, we need to know two things. First, we need to determine its number of electrons, which is also equivalent to its atomic number. Second, we need to know and follow the electron distribution mnemonic. So, this is what an electron distribution mnemonic looks like. As you can see, here are the subshells and the arrows. Just keep in mind that in writing the electron configuration, we need to remember and follow this sequence. Also, we have 4 subshells, the S, P, D, and F. The S subshell can hold up to 2 electrons. The P subshell can hold up to 6 electrons. The D subshell can hold a maximum number of 10 electrons. And the F subshell can hold up to 14 electrons. So, let's try this example. So, we have here the element potassium. So, using this electron distribution mnemonic, let's try to write the electron configuration of potassium. So, we know here that potassium's number of electrons is 19 because its atomic number is 19. So, therefore, all our superscripts must all add up to 19. So, starting off with 1s. So, we know that S can hold up to 2 electrons. Therefore, we are going to write 1s2. Next, we have 2s. Again, we're dealing with the S subshell, and the S subshell can hold up to 2 electrons, so we're going to write 2s2. Next, we have 2p. We know that p can hold a maximum number of 6 electrons. Therefore, we're going to maximize that number of electrons, so we're going to write 2p6. So now, let's count first all the superscripts. So 2 plus 2, that's 4. Plus 6, that's 10. But we need an overall of 19 electrons. So 19 minus 10, we need 9 more. So continuing, we have 3s. So again, s can hold up to 2 electrons. So we're going to write 3s2. For 3p, p can hold up to 6 electrons. So we're going to write 3p6. Now let's count first. 2 plus 2 is 4. Plus 6, that's 10. Plus 2, that's 12. Plus 6, that's 18. 19 minus 18 is 1. Therefore, we need 1 more electron. So, continuing, we have the subshell 4s. We are going to write 4s1. So, let's try to check if we got it right. So, let's try to add our superscript rather, and let's see if they all add up to 19. So, 2 plus 2 is 4. Plus 6, that's 10. Plus 2, that's 12. Plus 6, that's 18. And plus 1, that's 19. Which is equal to potassium's atomic number or its number of electrons. So, now from here, let's look at the valence shell or the outermost shell of potassium. That is the last part of its electron configuration, the 4s1. So again, our 4 here, we call it the main energy level. The S here, we call it the subshell. And our 1 here, our superscript, we call it the number of electron or electrons in that specific subshell. So just remember all these things because they're going to be extremely significant as we determine our quantum numbers. So now let's move on to quantum numbers. So quantum numbers describe the atomic orbitals and the electron properties of an atom. Just remember that quantum numbers describe two things, the orbitals and the electrons of an atom. So overall, we have 4 quantum numbers. First, we have the principal quantum number, represented by the small letter n. So our principal quantum number indicates the size of the orbital and the main energy level occupied by the electrons. So how? Here, let's look at this example. So we have here the Bohr diagram of the element sodium, the 11th element in the periodic table. So if the electrons occupy the first subshell, the nearest subshell to the nucleus, and also the smallest subshell, then our principal quantum number, or n, is 1. If the electrons occupy the second subshell, therefore our n is 2. If the electron or electrons occupy the third subshell, therefore our n is 3. So notice that as our n increases, the energy of the electrons and the size of the orbitals increases. Also, the greater the n, the greater the distance between the orbitals and the nucleus. Which actually makes sense, right? Because if our n is 1, therefore the electrons occupy the first subshell. That is the smallest subshell and the nearest subshell to the nucleus. On the other hand, if our electrons occupy the third subshell, our n is equal to 3. Therefore, that subshell is the farthest subshell from our nucleus and also the largest subshell. So how do we determine our principal quantum number using our election configuration? So here, let's have an example. So we have again here our element potassium, and we know that this is the election configuration of potassium. So to determine our n, or principal quantum number, we just need to copy the main energy level. So by looking at the valence shell, our main energy level is 4. Therefore, we just need to copy our 4, and there we go. We already have our principal quantum number. So next, we have the azimuthal quantum number represented by the small letter L. So our azimuthal quantum number corresponds to the shape of the orbital. So we have here our table. It says here that if our subshell or sublevel is S or sharp, then our L is 0. If it is P or principal, then our L is 1. If it is D or diffuse, then our L is 2. And if it is F or fundamental, then our L is 3. So how are we going to determine our L, or azimuthal quantum number, using our election configuration? Here, let's have again our example. We have potassium. Here is the election configuration of potassium. So to determine our L, or azimuthal quantum number, you need to look for the subshell. So by looking at the valence shell, here, our subshell is S, right? So looking at our table, if our sublevel or subshell is S, then our L is 0. Therefore, our L is 0. So pretty simple, right? So for the first two quantum numbers, we use the election configuration to determine them. Now, for the last two quantum numbers, we are going to use the orbital diagram. So the orbital diagram consists of boxes and arrows that represent the orbitals and number of electrons. So in our orbital diagram, just remember that the boxes correspond to the orbitals and the arrows correspond to the number of electrons. So this is an example of orbital diagram. So in this example, we have here two boxes. Therefore, this particular element has two orbitals. We also have here four arrows, two arrows up and two arrows down. Therefore, our element has a total of 4 electrons. So in writing the orbital diagram, drawing the orbital diagram rather, we need to follow and know these things. First, each box can hold up to 2 electrons only. Therefore, if we're dealing with the S subshell, we need to draw one box. If we're dealing with the P subshell, since the P subshell can hold up to 6 electrons, so 6 divided by 2, we need to draw 3 boxes. If it is dealing with the D subshell, we know that the D subshell can hold a maximum number of 10 electrons. Therefore, 10 divided by 2, we need to draw 5 boxes. If we're dealing with the F subshell, F can hold up to 14 electrons. So 14 divided by 2, we need to draw 7 boxes. Next, we need to draw all arrows up first before all arrows down. So how do we do this? So here is our example. We have here again our element potassium. So we need to draw the orbital diagram of potassium. So starting off with 1s2. So here we're dealing with the S subshell. Therefore, we need to draw one box. The S subshell here holds 2 electrons since 1s2. The superscript rather is 2. So we need to draw 2 arrows. So arrows up first before all arrows down. So 1, 2. Next, we have 2s2. So again, we're dealing with the S subshell. So 1 box and then 2 electrons. So 1 up, 1 down. Next, we have 2p6. So since we're dealing with the P subshell, we need to draw 3 boxes. So 1, 2, 3. Since 2p6, the superscript is 6. So it holds 6 electrons. So we need to draw 6 arrows. All arrows up first before all arrows down. So 1, 2, 3. So all arrows up first before all arrows down. 4, 5, and 6. So next, we have 3s2. Again, we're dealing with the S subshell. So 1 box and then 2 electrons. Arrow up, arrow down. Next, we have 3p6. Again, we have here P subshell. So we need to draw 3 boxes. So 1, 2, and 3. Since it holds 6 electrons, we need to draw 6 arrows. So all arrows up first before all arrows down. 1, 2, 3, 4, 5, and 6. Last, we have the 4s1 or valence shell. So since we're dealing with the S subshell, we need to draw 1 box. 1 box. And since it is 4s1, therefore, this subshell holds only 1 electron. So we need to draw only 1 arrow, and that is this one. So this is the orbital diagram of the element potassium. So remember this because this is going to be really useful later on as we identify the last 2 quantum numbers. So moving on, we have here the third quantum number, our magnetic quantum number, represented by m sub L. So the magnetic quantum number indicates the orientation of an orbital around the nucleus. So how? Here, look at this diagram. So here we have the S subshell. The S subshell has only 1 orbit. That is the red one. So since it has 1 orbit, its orbit is labeled as 0. For our P subshell, the yellow and orange ones, we have 3 orbits, labeled as -1, 0, and 1. For our D subshell, we have 5 orbits, the blue and violet ones, and they're labeled as -2, -1, 0, 1, and 2. For our F subshell, it has 7 orbits, That's from -3, -2, -1, 0, 1, 2, and 3. So, this information can be summarized through this table. So, we have here the 4 subshells, the SPDF, their number of orbits, and the ranges of their magnetic quantum number. So, how do we determine the magnetic quantum number using our orbital diagram? Let's take a look at this example. So, first, we need to label the boxes. So, how do we label? Here, take a look. So, for 1s2, we'll start off with 1s2. So, since S only has one orbit, therefore, we need to label it 0. For 2s2, again, one orbit, and that is 0. For 2p6, we know that P has 3 orbits, and they are labeled from -1, 0, and 1. Alright, we're just labeling the boxes. For 3s2, again, it has only one orbit, and that is 0. For 3p6, it has 3 orbits from -1, 0, and 1. And lastly, for our 4s1, so we're dealing with the S subshell. S has one orbit, and that is 0. So to determine our magnetic quantum number, we need to label our valence shell. We need to see where did our valence electron fell under. So since our valence shell is 4s1, therefore, this is the last part. So this is the box that corresponds to this valence shell. So since this shell is labeled as 0, therefore our magnetic quantum number is 0. So pretty easy, right? We just labeled the valence shell. We just looked where our valence electron fell under, and then we look for the label and copy that label. So next, we have the spin quantum number, or the M sub s. So it indicates the spin of the electrons. So if the spin is upward, or if the arrow is pointing upward, then our spin quantum number is +1/2. If it is pointing downward, then it's going to be -1/2. So how do we determine our spin quantum number? Here, again, we have our example. So to determine our M sub s, we need to look for our valence electron, the last arrow that we draw in our orbital diagram. So here, we have here our valence electron. So since it is pointing upward, it is spinning upward, therefore, our spin quantum number is +1/2. So, simple, right? We just examine where the arrow is pointing. If it is upward, then it is +1/2. If it is downward, then it is going to be -1/2. So, now let's have a few more examples. So, we have here the element boron, the 5th element in the periodic table. So, feel free to pause the video and solve for its electron configuration, orbital diagram, and quantum numbers. Okay, so since boron is the 5th element in the periodic table, therefore its atomic number is 5, and its number of electrons is also 5. Thus, our superscripts must all add up to 5. So following the electron distribution mnemonic, here is the electron configuration of boron. 1s2, 2s2, 2p1. So notice that our superscripts all add up to 5. So 2 plus 2 is 4, plus 1, that's 5. So our orbital diagram, here we're going to start with 1s2. So we're going to draw one box and then 2 electrons, 2 arrows. 2s2, one box again, then 2 electrons or 2 arrows. And for 2p1, since we're dealing with the p subshell, we need to draw 3 boxes. So 1, 2, and 3. And since it is 2p1, the superscript is 1, therefore it holds only 1 electron. So we only need to draw 1 arrow, like this. So now let's start determining the quantum numbers of boron. So starting off with N, or our principal quantum number. So first, we're going to look for the valence shell. Our valence shell is 2p1. Again, to determine the N, we need to copy the mean energy level. In this case, it's 2. Next, we have L, or our azimuthal quantum number. To determine our L, we also need to look at the valence shell and look for the subshell. So in this case, our subshell is P. Going back to the table, if the subshell or sublevel is P, therefore our L is 1. So we're going to write 1. Now, to determine our magnetic quantum number, we need to look at our orbital diagram. So, we need to label our orbital diagram. So, to save time, we're just going to label the boxes that correspond to our valence shell. So, since our valence shell is 2p1, therefore, the boxes that correspond to this shell are the last 3 boxes. So, we're going to label them -1, 0, and 1. Since our valence electron falls under the -1, therefore, our magnetic quantum number is -1. And also, since it is pointing upward, therefore, our spin quantum number, or m sub s, is +1/2. Alright. Pretty easy, right? Okay, now let's have our last example. We have here Einsteinium, the 99th element. So feel free again to pause this video and solve for its electron configuration and orbital diagram. Right. So following the electron distribution mnemonic, here is the electron configuration of Einsteinium. So if we add up all the superscripts, they're going to be equal to 99, which is the atomic number and number of electrons of Einsteinium. For its orbital diagram, again, to save time, we're just going to draw the orbital diagram for our valence shell, or the last part of our electron configuration, which is this 5f11. So since we're dealing with the F subshell, therefore we need to draw 7 boxes. So 1, 2, 3, 4, 5, 6, 7. Since our superscript is 11, 5f11, therefore we need to draw a total of 11 arrows. So starting off with all arrows up. So 1, 2, 3, 4, 5, 6, and 7. And then all arrows down, 8, 9, 10, 11. Okay, so this is the orbital diagram of the element Einsteinium. So to determine its quantum numbers, so first, we're going to make use of its electron configuration. So for our principal quantum number, again, we need to just copy our main energy level. In this case, it's 5. For our L, we need to look at the subshell. So in this case, it's F. Again, if it is F, or fundamental, therefore our L is 3. So for our m sub L, or magnetic quantum number, we're going to use the orbital diagram. So in our magnetic quantum number, we need to label our boxes. So starting off from -3, -2, -1, 0, 1, 2, and 3. So our valence electron is this, the one pointing downward. That is the last electron that we drew on our diagram. And since it falls under the box labeled as 0, therefore our magnetic quantum number is 0. Lastly, since it is pointing downward, it's spinning downward, therefore our spin quantum number is -1/2. So that's all for this video. I hope, guys, that you learned a lot and you enjoyed this tutorial. Thank you for watching!